Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on March 4th, 2026, just 3 days ago. It introduces a framework to train a critic model using sparse real-world interaction traces, achieving a plus 15.9 point improvement in best at 8 re-ranking on SWE-bench, and saving compute with 83% fewer attempts. The paper is titled, A Rubric Supervised Critic from Sparse Real-World Outcomes. And as we'll see later, the results are really impressive, with significant implications for training robust coding agents. Alright, Figure 1 outlines the core methodology for training this critic model. First, real-world interactions between users and agents are broken down into self-contained units of work, called segments. Next, the process extracts two kinds of learning signals. It generates dense critic rubrics, which are 24 behavioral features covering all the data, and combines them with sparse real-world outcomes, like whether the code was actually merged. Finally, these combined signals train a multitask critic model that predicts both specific features and overall task success, which helps improve applications like early stopping. So, Figure 2 breaks down how sparse real-world outcomes actually map back to specific agent actions through a 3-level hierarchy. At the top level, a pull request provides a broad success signal, like whether it was merged. This pull request contains a sequence of commits that track the specific lines of code edited and retained. Finally, these commits are traced back to individual segments within multi-turn human-agent conversations. This structure allows the model to assign fine-grained credit based on code survival, which measures exactly how much code from a specific segment made it into the final version. Okay, after Figure 2 showed how to assign credit, Table 1 reveals just how rare these success signals actually are. Out of over 150,000 total segments in the dataset, only 4% have code survival labels, and just 6% have pull request merge labels. This extreme sparsity means most real-world data lacks direct outcome supervision. Because of this, the authors introduced their 24 behavioral rubrics, which generate dense, usable learning signals across the entire dataset. Well, since Table 1 highlighted the lack of direct outcome labels, Figure 3 analyzes how the 24 rubric features actually correlate with success. The bottom panels look at benchmarks like SWE-bench and SWE-gym, where core agent failures, such as incomplete implementation or insufficient testing, consistently and strongly reduce the chances of passing a unit test. In contrast, the top panels evaluate real-world metrics, specifically pull request merge and code survival. Here, the effect sizes are much smaller and less consistent, which reflects the inherently noisier, multi-turn nature of real-world interactions compared to the clear-cut signals of academic benchmarks. So, while the previous figure mapped out those behavioral correlations, Table 2 brings it all together by comparing the final model performances. The first major takeaway is that models trained entirely without real-world data fail on real-world tasks, scoring below random chance with an area under the curve, which measures the model's ability to distinguish successes from failures of 0.48 or worse. However, when the authors apply their success plus rubrics approach using the code survival objective, performance jumps significantly. On the SWE-bench dataset, this rubric-supervised model achieves a best at 8 score of nearly 74%, which is a massive leap over the 58% random baseline. It also excels at early stopping, requiring only 1.35 attempts on average, compared to 8 for random selection, saving a tremendous amount of compute. Alright, after the previous table established overall performance, Table 3 explores generalization across different large language model backbones. The success-only baseline overfits heavily to Claude Sonnet 4.5 and drops below random chance when evaluated on Claude Opus 4.5. In contrast, the rubric-supervised model maintains positive gains across both backbones, achieving an almost 16-point improvement on the combined set. This proves that rubric supervision captures transferable behaviors rather than specific model artifacts. Okay, while Table 3 focused on generalization, Table 4 shifts to training time data curation. It reveals that randomly selecting real-world segments for supervised fine-tuning actually decreases performance compared to the base model. In contrast, using trajectories selected by the critic pushes the resolve rate up to almost 48%. Finally, filtering directly by true code survival outcomes reaches roughly 50%, which acts as an approximate upper bound, proving that critic predictions generate actionable training signals. Well, wrapping up, two key takeaways stand out. Process-based supervision bridges the gap between clean academic benchmarks and messy real-world deployments, and grounding sparse outcomes in dense behavioral signals unlocks vast amounts of previously unlabeled data. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.